I think this is the lecture number 2, right?
Yes, sir.
So last lecture we saw about Huygens principle. We got the idea of wavefront. We got the idea of secondary source, primary source. Also, we understood something about phase of a wave. So today, okay, those basics we are going to again use in the chapter of wave optics, but we have to deviate from there, and we have to go back to the world of atom. So the old model of atom, as you know, like Thomson or Rutherford. So in the Thomson model, there is no idea of orbit and all. It is like a plum pudding model, as you know, from class 9th to 10th. And in that model, what they assume that the entire charge is spread out throughout the volume of the atom. And so you can say the positive is spread out the volume of atom and the negative is like a seeds of the plum. Okay. So that was the plum pudding model by the Thomson. So that's called the Thomson model. So definitely I'm not going to teach you Thomson model, but we can solve some question based on Thomson model and electrostatics. So in Thomson model, do we have a specified location of electron, or is it spread everywhere?
Electron is localized charge but randomly distributed.
Yeah, so it's like a charged particle which is randomly distributed, right? So for the sake of simplification, if I talk about only single electron system, so that single electron can be anywhere, isn't it? So single electron can be here, 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 anywhere. So if an electron will make transition within this Thomson model, then what kind of frequency will be emitted in the surrounding? Okay, so here also, because everywhere, if I assume this as a positive charge cloud, or if you assume this as uniform distribution of positive charge, so let's say the entire atom is representing a positive charge. So positively, let's call this as positively charged sphere. For the sake of symmetry, I am assuming the entire positive charge is spread throughout the volume. Because that time, if you remember, that time the idea of nucleus was not there, right? So saying that positive is in the nucleus is not a correct idea. So in Thomson model, what we do? We assume that the positive charge is spread throughout the volume. I hope this is clear to all of you. So
Yes.
you can think this as a positive charge sphere. And we have just one electron. Okay. So this single electron can be anywhere. So I'm assuming at a distance r from the center. So we have a negative charge. Okay. So we have single electron. Okay. So what is the force acting on this particle? So we know that inside the uniformly charged sphere, the electric field will be readily outward. So if the electric field is in this direction, the force on the negative charge will be, let's call this as E in value. So how much force will act on this electron?
E.
E into E. What is the value of E, by the way? Assume the density of charge as rho. As of now, you can think as rho. And you can assume
Rho R by 3 epsilon naught.
Rho R by 3 epsilon.
Yeah, very good. So E is actually rho R by. So the force acting on this electron will be towards the center, because we know field is radially outward, so force will be radially inward because it's a negative charge particle, and therefore the answer turns out to be rho into E value wise. So in vector form, we can write an acceleration vector equals to minus A by M. Yes or no?
Yes.
Can we
Yes.
write? So A turns out to be minus rho E by 3 epsilon naught M E into R. And if you remember, this represents the standard equation of simple harmonic motion SHM, because A is proportional to displacement from the mean position. Here mean is the center itself. Do you realize this?
Yes.
And the standard equation is omega square R. So if I call this as equation 1 and this is equation 2, if we compare, so comparing equation 1 and 2, the omega square we can write as rho E upon 3 epsilon naught me. So omega equals to how much? So the frequency of the wave will be, you can add frequency equals to omega by 2 pi. So you can add as 1 by 2 pi. And therefore, if we consider that, okay, that transition will also create energy in accordance with the Planck's law, which is not applicable in the Thomson model. But imagine if Thomson model is connected with the Planck's law. Okay. Hypothetically, of course, don't take it seriously. Okay. So if we connect Thomson model with Planck's law, then energy of radiation we can add as HF, if you remember. So such hypothetical situation will create a radiation of energy H into how much? How much is that? Okay, 1 by 2 pi under root rho E by so this is the energy of such radiation which occurs inside the Thomson model hypothetically. Okay. But of course, so Thomson model, I'm not going to teach you Thomson model. You know about Thomson model, plum pooling model. But we can really have a really nice question from the Thomson model as well. That's why I just want to discuss. Okay. So after Thomson model, which model we need to study? So if you remember the Rutherford model, let me tell you something about the theory behind this model. So classical physics says that electron is orbiting the nucleus. So any particle which performs a circular motion will always have the acceleration because it is changing the direction. So even though you maintain the speed, your velocity vector will keep on changing. So can we say such particle as accelerating particle?
Yes, sir.
Yes.
Now classical theory says, not I'm saying, classical theory says that every accelerating charge must radiate energy. Okay, so as per, like type it. As per, just a moment. Classical physics, every accelerating particle will radiate energy, hence orbiting electron must lose, spelling is lose, must lose energy and hence should eventually collapse with nucleus, isn't it? So classical theory predicted that that every orbiting electron must radiate energy, must lose energy, and because it will lose energy, so it will lose velocity also, because half mv square, as you lose energy, half mv square will be lesser, and if half mv square will be lesser, then mv square by r will also be lesser. So centrifugal force will also decrease, and if centrifugal force will decrease, then nuclear force will become more and more. So eventually every charged particle should spiral towards the nuclei, and that will make an atom unstable. But contrary to that, we know that atoms do exist. So from classical theory, it should collapse eventually because of the loss of energy. But this is not found. Okay. So the Rutherford model of atom was rejected on this ground. Okay. Because of the way classical theory explains the energy relation. So that is why we came across the which model?
Bohr's.
Bohr's model. So we came to know about the Bohr's model. And mind you that these are models. Model is the, you can say, human imagination which fits the phenomena as exhibited in nature. So you create some hypothetical idea, and through that idea, if you are able to explain what is happening to a certain extent for a variety of situations, then that model is accepted. And then if it is accepted, then you get the Nobel Prize also. That's a byproduct of getting a acceptable model. So models are basically our own imagination, our own idea, the way we would like to visualize the world. And Bohr also had some idea. So he established something called the stationary orbit model. Okay, so the Bohr's model is also called stationary orbit model. So as I said, Bohr was also working on light. So he got the spectral light of H atom. So he obtained the hydrogen spectrum. And after obtaining the hydrogen spectrum, he got 4 missing lines. If you remember the last lecture, it was H alpha. So in the H spectrum that he obtained for the natural light. Okay, so natural light means light coming from the sun. So when he let the light of the natural light of the sun going through the chamber containing the H atom. Then he obtained the spectrum, and in that spectrum, he observed some sharp, dark band, or you can say missing lines. And he named this missing line as H alpha, H beta, H gamma. Okay. And he had the numerical value for all these missing lines. So he went to his friend. The name of friend was John Jacob Balmer. Yeah. So he went to his friend John Jacob Balmer and he gave the missing values to his friend. And as the legend says that within half an hour, or maybe some time, he came up with the formula. And that formula later on become the Rydberg formula, which we'll come to know eventually. So he gave a formula which was discrete in nature, in which if you substitute 1, 2, 3, 4, you get all the answer. And that was the first step towards the establishment of quantum theory. So Bohr said that, okay, electrons are permissible to revolve only in those orbit, or you can say space, where the energy is constant. It means orbiting in those space will not let you radiate energy. So that's very interesting. You're somewhere creating a new theory because all the existing theory of physics was not adequate to explain this behavior. So whenever something happens like this, you need to create a new theory, new principle, and that was the foundation of quantum theory. Okay, so quantum theory, as we know today, was kind of the need of that time to explain the event which was not able to explain using the established classical theory of physics, especially the physics by the Newton. So anyway, you can say these are the pioneer of quantum theory. Quantum is the discreteness. So what is orbit? What is the Bohr's postulate? Let me give you the Bohr's postulate. Tell me guys, what is Bohr's postulate?
An electron can revolve around the nucleus in atoms in which the angular momentum is an integral multiple of h by 2 pi.
So that was the second postulate. What is the first postulate?
Sir, only applicable for one electron atom.
Yeah, that is also okay. That's a single electron system. Yeah. So the first postulate was electrons are permissible to orbit, it is permissible to move in those orbit in which energy remains constant. Okay. So this was the first postulate actually. I mean, electron cannot move in any orbit. You're only supposed to move in that space, or you can say orbit, in which your energy remains constant. You do not radiate by virtue of motion in that space or by virtue of motion in that orbit. So that is the first postulate. And second is what you said, that the orbital angular momentum of an electron moving in those orbit must be quantized. Okay. So, and why the word quantized? Because since you are getting a discrete value of energy, so discrete value of energy corresponds to the discreteness of energy existence as well. Okay. So let's say if you go to ATM and if you want to withdraw money, and if your requirement is, let's say, 100 rupees and 125 rupees and 60 paise, the ATM won't be able to give you that money. So the denomination which you can get from the atom is fixed, either it's 100 or 500 or maybe 2000. So the transition can only happen in the discrete values. So you can get either 100 or 200, but you cannot get 150 because of the denomination is discrete in nature. Similarly, if we are getting some missing lines which are having very discrete and they are multiple of some number, it means this discreteness is representing that the way energy is composed within the atom itself is discrete, because only discrete transaction can give you discrete answer of energy. And that was the idea behind the Bohr's theory, that he was able to understand that these energies are actually in discrete values, and they are arranged in some order. The order he actually envisages as a orbit. So orbit is basically his own idea of order. Okay, you can say that electrons, sorry, the angular momentum of orbiting electrons are, or you can say each, is quantized. So quantized means basically discretized. So it is having discrete value, some specific value, not all values. So when we say non-quantized, it means it is continuous in nature. Quantized means you have some specific value, but you don't have all values. So that is the basic postulate of Bohr's theory. But if you go even more deeper into the establishment of this postulate, you need to go through something called the concept of stationary wave. So I'll try to introduce you the idea of stationary wave, which you will study in wave and sound chapter, or you might have studied it. So we know that electron will exhibit the particle-like behavior, but there is also a behavior which is called a wave-like behavior. So later on in the development of quantum theory, de Broglie established the fact that even a particle which is known to the world, because electron was basically established as a particle in the beginning. So the particle can also exhibit like the wave-like behavior, and therefore a mathematical wave was introduced, and this mathematical wave is basically called the probability wave. Okay, and please do not try to think of something of physical wave. So there is no physical wave at all. It's called probability wave, or you can say that if you plot a graph, a 3D graph in which every point will have some value to exhibit, some probability to exhibit, then if I try to map the intensity, or you can say the value of probability by some shade. Okay, so let's say if the higher the probability, more the darker shade, and lesser the probability, lighter the shade, then that mathematical function will look like this. Okay. So we need to understand the concept of wave. So wave is like in physics we study wave as some sort of disturbance, but in quantum world the wave will become mathematical in nature, and because it's mathematical we represent by something called complex number notation, and because complex number will have no meaning, so you square the complex number, you take the conjugate, because if you multiply a number complex number with its conjugate, what you get is a real number. Okay, and that is why the Schrodinger equation, which you call psi, is a complex wave, but when the moment you take the science square, it's called the probability actually. Okay. Because it's a real. This is real, and this is complex. So it is purely a complex number notation which we use. So imagine that as a physical wave to understand the idea. Okay. So just to remind you how the discreteness of energy is created. So for that, we need to understand something called mode of oscillation of a string. Okay, so you can just think of a string. And if you think this string is a part of a guitar, maybe some, so that is the wire which you plug it. So when you plug this wire, it will start into vibration. So in the simplest form of vibration, it will have just one NT node and two nodes. So you can say this is called node, and this is called NT node point. This point is called NT node basically. So in the simplest mode of vibration, so when you plug in, it means you're supplying some energy, and that energy is actually represented by this oscillation. So this oscillation is representing the disturbance which you caused by single plug. So you took a, that maybe your finger or a plug which comes, and if you just, push it aside and release it. So pushing it aside means you're supplying some energy, and releasing means you're letting that energy to show the effect on the particle of the medium. So every vibration represents one discrete amount of energy, which is the energy, of course, confined within this distance, this length of the string. So a vibrating string represents one finite amount of energy if it is a standing wave, if it is not a traveling. So when you establish a standing wave between two fixed nodes, then you can also give a different amount of energy. So as you increase the amount of energy, what will happen? So as you increase the amount of energy called the mode of vibration, or also called excitation. In atom world, we call excitation. Okay, so excitation is like the mode of vibration. So here we have the, let's say, fundamental mode. So a higher excitation actually represents higher mode of vibration in the concept of standing wave. And this we can represent something like this. So instead of one loop, we are going to make two loops. So there's nothing like a loop, it's like the mode of vibration. So string will vibrate in such a way. So this way of vibration means you have given more energy, and that will also represents the excitation, the excited state of the probability wave. You can call this is the excited state of probability wave, and the way Bohr depicted, because this is happening after Bohr, created all those ideas. So this standing wave was already the idea, existing before, but the quantum behavior was actually explained with the help of standing wave. Okay. So the stationary wave or standing wave is a way to understand the quantum nature of energy. So every vibrating string, okay, every vibrating string, just Okay. So a standing wave actually represents a finiteness of energy, and different mode of excitation gives you the different amount of energy. And you can think the different amount of energy as the different orbit. Okay, so one orbit is representing one finiteness of energy. So second orbit is representing the second finiteness of energy. So every orbital represents some finite value of energy, and that is how we define the excitation. Okay, so we call the electron goes from the ground state to excited state. So this way of saying is similar to that. You change the probability wave from the fundamental mode to the first, you can say, overtone or second mode of vibration. So this is how we can correlate the two ideas. Okay, so quantum idea and oscillation of string are always correlated. Okay, so this is how the idea came into picture about the quantum of energy value. So if you understand the string part, probably you will also understand the Bohr's postulate easily. Okay. Now, from the theory of wave, the separation between the two nodes represent half of wavelength, right? So if I call this length as L, so in the first vibration, what is the separation between the two nodes? L, and two consecutive nodes represents half of the wavelength. Okay, you can also understand this way. So if you draw any single wave from this point to this point is called lambda, isn't it?
Yes.
Crest to crest you call lambda, so all are lambda only, no? So from this point to this point we can call lambda by 2. So if I repeat the same wave above and below, you can see this is the idea of standing wave. So from one node to the next node, what is the distance? Lambda by 2. Okay. So from this node to this node, the distance is lambda by 2. From this node to this node, it is again lambda by 2. And this entire length is L. So you can say lambda by 2 plus lambda by 2 equals to L. So lambda is how much? L. Okay. Now, if I vibrate a string in general nth mode, okay. So what happens if we oscillate a string in nth mode? So how many such loop will we form, guys? Tell me. So if it's some nth mode, okay. So in nth mode of vibration, you will see n loop, because you can see first mode will have one loop, second will have two, then third will have three, then fourth will have four. So nth mode of vibration will give you what?
And
N loops.
N loop, and every loop is of what length in lambda?
lambda
Lambda.
Lambda by 2. So n lambda by 2 equals to L, and therefore we'll get a lambda equals to 2L by n. Understood? Now, the nth mode of vibration is basically n minus 1th excitation, because first excitation means second orbit, right? What is the meaning of first excited state?
Second order.
second order.
So second excited state means,
Third order.
so n minus 1th excited state means
And third.
nth orbit. Now, in this diagram and in atom, what is the problem? Okay, if you look at this diagram, the length of the string is finite. In atom, as you go away from the center, the size of the orbit will grow in value. Do you realize this? So as you move away from the center, you will get bigger and bigger orbit. Yes or no?
Yes.
You can
Yes,
imagine that orbit as a string. Imagine that orbit as a string, and imagine that a mathematical wave will be established in that string. Okay. So as you go away, then as we increase the mode of vibration, we also vibrate a bigger and bigger string actually. So you can think every orbit as a one string. So what is the size of the string of nth orbit, or in general any orbit? So
2 pi.
2 pi r. So if I choose any orbit, let's say the in general orbit called the Rn, is if Rn is representing the radius of nth orbit, Rn is representing what? Radius of nth orbit. Okay, which means n minus 1th excited state space, you can say. And how we create the standing wave? So in a finite string, the way to create a standing wave is you send a wave along the string. The wall will create a reflection of the wave. And when the reflected and the incident wave superimpose to each other of same amplitude and same frequency, then we have standing wave, or in a way you can say energy gets confined, or energy get discrete, or you can say discretely distributed. So whatever you can say. Similarly, if I imagine this closed path as a path in which we can create a disturbance. So let's say you make a punch here. So once you punch, or imagine there's a disturbance will travel in both directions, right? Here as well as here. Do you realize this?
Yes.
So disturbance will
Yes.
travel in both directions. So they are bound to meet at some place. So because of symmetricity, where they will meet? Because of symmetricity, they'll meet at the midpoint, diametrically opposite point. Yes or no?
Yes.
Yes.
And because they will meet at a diametrically opposite point, then the half of the perimeter will establish a standing wave like this. Okay, I'm not doing exactly, but you can understand. Okay. So this way of a representation, if you have seen in some textbook, is actually a way to represent a standing wave. And because in the nth orbit we get the meaning of nth orbit means we get n of number of loop is n. We call the, let's say n is the number of loop. So n lambda by 2 we write as equals to pi r. Why pi r? We are taking only half of the length. Okay. So n lambda by 2 equals to pi r, because we consider only half of the length as a vibrating part, and we write the equation for that part. So n lambda by 2 we write as pi into r, and therefore the n lambda becomes 2 pi r. Now from the de Broglie postulate, assumption from idea of matter waves. I hope you have studied in chemistry matter waves. Yes or no?
Yes.
So from matter wave, what we know, the lambda is equals to how much? H by P, the momentum.
Yes.
So Planck's constant upon momentum is called the de Broglie wavelength, or you can say de Broglie wavelength, or a wavelength of the matter. So you can think that electron is a particle, so it will exhibit not electromagnetic wave, it will represent the matter wave, right? And since we are converting an electron into a wave kind of structure, so we have to take the matter wave into consideration. We cannot take the electromagnetic wave. So because it's a matter wave, we can write H by P, and therefore this lambda is representing the de Broglie wavelength or de Broglie wavelength. If you substitute, what you get? N H by P equals to 2 pi r, and therefore P into r equals to NH by 2 pi. And P you can also write a mass into velocity, so you can write mvr equals to NH by 2 pi, and that's why this is called the angular momentum. And the n is representing the discrete value, h by 2 pi is some fundamental constant. And because angular momentum is n times something fundamental, so this is called the quantization rule. So that's why the angular momentum here is, this is a quantization rule of angular momentum of orbiting electrons. Understood? So this is this is the postulate of the Bohr's second. I mean, this is the Bohr's second postulate, and this is the informal proof, I would say. So now you know that this entire idea of this quantization is coming from the idea of standing wave. Understood? So standing wave is a way to understand the quantum behavior. Okay, so if you want to understand quantum behavior even in future, in advanced level, the only way we understand is through the standing wave derivation. So advanced physics or mathematics will take care of all this thing, which you can study in higher courses. So second postulate is clear?
Yes.
Okay. Now, because the Bohr, first of all, let's start to understand for what kind of atom this Bohr's model is applicable. Okay. So Bohr's model is applicable for what? Tell me, guys.
Hydrogen-like atom, single electron species.
Single electron system. So because it is applicable for a single electron system, it means for a hydrogen it is always applicable. But helium will have how many electrons? 2 electrons. So how to make it single electron?
Helium
By
plus.
removing one of the electron. That's simple. So hydrogen, helium, He plus. Then lithium will have how many? 3. So we have to take Li plus plus. And for beryllium, so Z is how much? 1, 2, 3, 4. Let me tell you that if you are solving Bohr's theory, and if some option will have the answer H, E, Li, B, it means nothing can go beyond this. Your answer must be out of these 4 elements. That's it. In any Bohr's theory question. And if they somehow mention only one of the option and other options are not out of these 3, it means that will be the answer anyway. Okay, so this is only applicable for a single electron system for some reason. I'll come to that also, why we only apply the single electron system. Then we move to the X-rays later on. So in the atom, we have a nuclei. Needless to say. And this nucleus will have some positive charge. Depending on which element you choose, the charge within this nucleus will be how much? Z times C, because Z means number of protons. What is definition of atomic number? Atomic number is
Number of protons.
number of protons. Okay, very good. So that's simple. That's number of proton. You know this. It's nothing big deal. But we have only one electron system. And I have no idea where the electron is, in which orbit. So I will call this as Rn. I have no idea with what speed it is orbiting. I call Vn. I don't know what is the angular frequency. I will call omega n. I don't know what is frequency, so I'll call Fn. So in terms like this, you can use n as a subscript to represent the general orbit idea. Okay. So I'm not representing first orbit or second orbit. I'm representing some general orbit. And because this is the curvilinear motion, because electron is a particle, so you can think as a curvilinear motion, or you can think electron is connected to the string with the center and is performing angular motion. So you can also solve using the the rotational idea. So there are ways of writing things. So let me show you that how you can write things. So the kinetic energy of the electron in the nth orbital will be how much? Half m Vn square, correct? But
Yes.
what could be the other way of writing? P square by 2m,
Omega is
the momentum, isn't it? And what could be the other way of writing? The angular momentum square by moment of inertia. And other way of writing?
half I omega square.
See, these are 4 ways in which you can write the kinetic energy. So no need to use only half m square all the time. Whatever is convenient, you can use it. Okay. Now let me show you how to write the potential energy, which is pretty easy. From electrostatics, we know potential energy will be how much? How to write the potential energy of two charge particles?
K ZE square by Rn.
No, it's wrong.
Would be minus.
Minus, correct. So minus K, because one charge is positive, other is negative.
Yes.
So potential energy will
Yes.
be negative. So minus K, which is the unit, 1/4 pi epsilon naught. And then ZE square, because ZE into E upon Rn. So this is the potential energy for nth orbit, of course, because we are using the Rn formula. And for every curvilinear motion, we do have energy equation, but we do also have something called force equation. So what is the force equation here? The force equation is, so for any orbiting electron, what force equation you can write?
M omega square.
So net centripetal force equals to m omega square r, mv square by r, whatever you want to say, or you can say centrifugal force equals to attractive force and whatever. So there are ways of saying or writing, because you know circular motion, and if you really understand circular motion, you should write this easily. So what is the net force towards the center? You can say MAC. So net force towards center is how much, guys? Net force towards center is E times E. That's it. Charge into electric field due to nucleus. Okay, why we should not write K Q Q2 by R square? Of course you can write, because here E will have that formula also. But the way you should write is E times E, because in examination they may give you that the nucleus is creating electric field of this value. Instead of giving the charge of the nuclei, you have to start with this equation, E times E. Okay. So E times E equals to M, and AC you can write as Vn square by Rn. There are many ways of writing, as I said. And this is the electric field, so we can write the electric field of the nuclei. So what is the electric field of nuclei? If charge is known to you,
KQ by R.
K,
KZE by R.
now in JEE advance, never ever mug up any formula which you have studied in chemistry. In JEE advance, you need to know the basic idea of circular motion. That's very simple. You need to know how to write the circular motion equation, net force equals to mass into centripetal acceleration. You need to know how to write the kinetic energy and potential energy. In JEE advance, you have to manipulate things from basic. Okay. So you also proceed in a similar fashion. And if you have studied the electrostatics, you know how to write all those things. So basically the idea of electrostatics and the laws of motion together will give you all answer. Don't try to mug up any formula. Okay, it will never help in advance. Okay. Now, apart from the energy relation, force relation, which relation is extra here? Because we need to express
State
every
relation.
answer in terms of quantum number. So the quantization rule will always be applicable, right? So we have to use the, as long as it is Bohr's model, the quantization rule will rule here. Okay. So once you know how to write energy, once you know how to write the force equation, the third is called the quantization rule. And unless you're not going to write this, you cannot express your answer in the desired format. Okay, so what is the quantization rule? We have seen this. M VR equals to NH by. I mean, there are many ways of writing. I'll show you in how many ways you can write. Okay. But again, you can get rid of the energy rule and the force equation. That is not required. Why it is not required? Let me show you. So if I go with the classical Bohr's model, like the Bohr's model without any modification, as you may see in case of JEE, if it is really the old one, the classical one without any modification as per the JEE syllabus, your force equation, if I rewrite, what will see? K ZE square Rn square equals to M Vn square by Ra. Right, guys? And this will cancel out. Okay. So
Yes.
mv square, you're getting how much? So half mv square is how much? So kinetic energy is always expressible only in terms of radius. No need to have velocity. So orbit will determine the kinetic energy also, and orbit will determine the potential energy also. That is why we never try to mug up any of this. The potential relation was how much, if you remember?
Minus KZE square by
Is
R.
it where?
So you can clearly see the kinetic relation and potential relation having something common. The K is Z square by Rn. Do you realize this?
2 times K
Yes.
minus.
So kinetic energy is written as mod of U by 2. This is the famous relation for the old classical Bohr's model. And not only for that, for any orbiting charge, this relation is always applicable. So for
This is like in
every
gravitation we
orbiting
have
charge, pardon?
in gravitation also we have done this.
Yeah,
Right.
we can.
Right.
Yeah, we have done this in gravitation as well. So this relation is applicable everywhere. So you're not supposed to write the force equation and write the kinetic energy and all. See, if you know the potential, because that is the easiest way to write. The way, the thing that you need to realize that all these equations will lead to this relation directly. So I need not to go back to all those derivations. So you can skip force equation for sure. You can skip the kinetic energy equation for sure. So the way to solve question of Bohr's theory is simply you write the potential and you're done. So what you are supposed to write is potential and quantization rule. Okay. So how to get to the total energy part? Because that formula is very simple. So total energy will be how much? Which we write as E. Total energy. For any orbiting electron, if you want to write the total energy, what will do? You will add its potential and kinetic both, right? Isn't it?
Yes.
So kinetic you can write as kinetic you can write as minus U by 2, because U itself is negative. So can I write minus U by 2? Okay. This is minus U by 2, isn't it?
Yes, sir.
Either
Yes.
write mod U by 2 or you can write minus U by 2. It's the same thing. Yes or no? Basic
Yes.
maths, come on.
Yes, sir.
And potential is U. So I need
Yes.
not to remember anything. See, if I know only potential, I can get every answer. So the total energy itself is how much?
U by 2.
U by 2. Total is half of the potential. This is again a formula. So what is interesting to note here, that we can actually get rid of a lot of calculation if you just remember the total is half of potential and kinetic is minus half of potential. That's it. Very simple. So what we really need to know to solve question of Bohr's theory? What we really need to know? Tell me. We need to know potential and quantization rule. Do you realize this?
Yes, sir.
And now you can clearly see the total energy turns out to be how much? U by 2, which is minus kZe square by 2Rn. Am I right?
Yes.
What is the significance of negative sign here? If the total energy of any orbiting electron or any charge is negative, which means it's a bound system. Total energy represents the bound system if it is negative, and it is unbound if it is positive. It means it is bounded by nature because it is in debt actually. Negative means you are in debt. So you have taken loan and you cannot leave the country. So you're not free actually. So how to make it free? To make anyone free, we have to make it unbound. And how to make it unbound?
Give it energy.
Give it the energy equivalent of the negative value. Simple. Or more than that, of course, but the minimum we talk about. So we talk about the whatever negative energy you have, that is like the debt. So to make you free, I need to supply that energy. So when you supply that energy to the outermost electron, that process is called ionization. That's very simple. It's basically you're making a bound system free actually. So this electron is bounded electron. And to make it a free electron, I need to supply that energy. And if you belong to the outermost orbit in the configuration of electron, as you know, then getting that energy will make you free from the system. And so this process is ionization. But if you're not in the outermost orbit, if you're in some other orbit, then to make you free, I need to supply energy more than ionization. Yes or no?
Yes.
Yes.
And the moment we go from the atom to a metal, so metal is single atom or collection of atoms? A metal represents what? Collection of atoms. So is it isolated atom or it's a, you can say, lattice of atoms? It's a crystal or collection of atoms, right?
Yes.
Bohr's theory cannot be applied for the collection. It is only meant for the isolated gaseous atom. Single electron system along with isolated gaseous atom. So don't try to apply Bohr's theory in atom if it is a part of a molecule, if it is a part of a crystal. Okay. Because in molecule you apply the molecular orbital theory, MOT, because it will not follow the same rule of Bohr's. If it is part of the crystal, it will not follow even the molecular orbital theory. It will follow some other rule actually. So everywhere, the way atom is, existing in nature, depending on the configuration, the God has different energy, given different energy configuration, and therefore all will not be same. The formation of crystal is accompanied by release of tremendous energy. So you can imagine a crystal to be in a real debt. I can say tremendous debt. So for them to be free, it's even more difficult. Okay. So things are quite different in different situations. But in crystal, what happens? The energy released during the process of creation by the God. Of course, we have not created. So in the process of creation by the God, energy was released so much that most of the electron already left their outermost orbit. So where they were residing? In the lattice gap actually. I hope you all have studied the solid state in which you have seen the void.
Yes.
Huh? So void is part
Yes,
of lattice gap, isn't it?
Yes.
In the creation of crystal, electrons left their outermost shell but they are part of the void or the lattice. And to remove that electron lying on the superficial layer, you can say the surface layer, the energy requirement is even lesser because they are free from atom, but they're not free from the lattice. So atom freedom is done. You have to free from the lattice. And when you supply the energy to free from the layer, the lattice, we call it a work function. Understood? So work function is a different thing. Ionization is a different thing. Every term will have some context. And Bohr's theory is only applicable for the isolated gaseous atom, not for any atom or anywhere atom in any situation. Atom, if isolated, will follow it. If it is not isolated, it will not follow it. So I hope this is clear to all of you, how atom
Yeah.
behaves in different situations.
Yes, sir.
Yes.
Yes, sir.
So Bohr's theory, molecular orbital theory, and work function, or you can say photoelectric effect, all three are very distinct process. Do you realize this? Okay. And that's why we study separately. Anyway, so once you get the energy as a function of R, that is not our requirement. What we are really looking for? We are really looking for the quantum relation. What does it mean? We would like to express everything in terms of principal, quantum number, and constants, right? So how we would like to express things? In terms of principal quantum number. No principal quantum number? N.
Yes.
Yes.
So the quantum number is like the address. Yeah, I hope you know this. So every term is representing the more specific address. So principal quantum number is like, let's say if I ask you where you stay or in which city you live. So you can say, okay, someone is living in Bangalore, someone in Mumbai. So that's the first stage. But just by saying that you live in Mumbai, can I reach your home?
No.
So you need to give me more specific information. Okay, so you will say, okay, this is my postal code. So I'll come to that city, I'll search for that postal code. And in that postal code, I will get many buildings. You will say the building name actually. In that building, there are many flats. You will say flat name, then I'll reach your home. So all the four quantum number, principal, what is next?
Angular.
Angular, then azimuthal, you can say,
Magnetic.
then
Magnetic and
Spin.
and spin. So
Spin.
these are like, yeah, you as you go from top to bottom, you go more precisely, try to exactly, because even if you reach to the orbit, you will see there in one box, there are two electrons up and down, the two opposite spin. So to locate the exact electron, you need to give the spin also. So these quantum numbers are like the address verification process within the atom world. So atom is like a universe, and these quantum numbers are basically the way to locate the address. Okay, so we are trying to understand this energy relation, although not very precisely, but up to city level actually. And that is why we are trying to understand this energy behavior only up to the principal quantum number wise. I hope I'm clear what I'm saying.
Yes.
Okay. So once you get the energy, you want to find everything in terms of principal quantum number. So knowing the city, can you find how far you are, like what is the distance, what is the radius? So you have the total energy relation, how much? Once again, minus k ZE square upon twice Rn. In your mind, you must write the potential and divide by 2. That's it. If you're doing this part or this kind of calculation, it is very easy for you. So in fact, deriving the energy relation is quite easy. I'll come to that, how to derive it quite easy. Okay. And what is the quantization state? L equals to NH by 2 pi. Okay, guys. So let me show you energy derivation in one line. So we can write L square by 2y equals to what? What is this? Kinetic energy, right?
Kinetic energy.
Yes.
Yeah. So if I put a minus sign, what will get?
Total length.
Total energy. Yeah,
Total.
exactly. So anyway, let me write down this L square 2I is how much? N square H square by 4 pi square, and I means, oh, this is L square by 4 pi upon 2I by 2I. I moment of inertia is how much of a particle at a distance r? M,
MR.
MR.
isn't it? So what we can write? Tell me, guys. I need total energy, na? So I can add total energy is how much? So there are two ways of writing total energy, right? You can see the En we can add by minus, am I right? So this
Yes.
way of writing or this way of writing are same thing, no?
Yes.
See one line,
Yes.
we got the derivation in one line over. So can we write KZE square by 2Rn equals to N square H square upon how much? 8 pi square. Sorry. ME Rn square. Is this clear, guys? No.
Yes.
Yes, sir.
Yes. Okay. So it's done. We got the answer. What is Rn then? Rn equals to 2, 4, 8. Rn go this side. N square H square upon 4 pi square M
KZ
KZE square. But let's write K also, right? What is K? So we got Rn equals to how much, guys? Epsilon naught H square upon how much?
N square.
Oh, that will write later on. Pi Me E square whole into
Square by
N
Z.
square by Z. How difficult is the derivation of radius? Is it very difficult?
No.
It should not be. It's very easy actually. If you really understand the energy way of writing, it is hardly one line activity. Even it's a very complex relation, but it technically takes just one line. And this entire term we call A naught or A maybe something. So this is the smallest radius possible. So this is the ground state radius of H atom, right? So that's why this is the smallest value, A naught N square by Z. And if you want to calculate this A naught itself, you can do this here. So generally don't do, what you do is you simply derive it. I mean, remember the answer. How much is this?
0.5.
0.53.
So 0.529 angstrom, right?
Yes.
Okay, sometime remember this calculation also. So you in JEE, even you need to use this relation to do the calculation and so on. If you really want to be good with modern physics in physics part, don't remember any formula. If you can derive it, you know the chapter. If you don't able to derive it, leave the chapter, because most of the question will not work if you only remember the formula. It will not going to work actually, except for some cases. We'll come to that. Oh, great. So you got the radius. Can you get the energy quickly? You're free to substitute Rn. either in equation 1 or equation 2? I would prefer 1, isn't it? Because we have to substitute Rn. In 2, the problem is I have to substitute Rn square. So which one you will prefer?
1.
First.
First. So can you substitute and tell me the
First.
answer? Do it. Go ahead and substitute the answer. Okay, you can derive and then substitute. That's a good homework. I mean, good practice right now. So derive the radius first. Everyone, derive Rn. Let's see who can derive faster, fastest. Done, guys?
Yes, sir.
Sir, just a second.
So those who have derived, raise your hand.
Yes, sir, done.
Okay, so you should derive this first. So what is Rn coming? Tell me. Darsh, tell me how much you got.
Sir, e raised to 4 me upon 2 epsilon naught square h square.
E raised to 4.
Ah.
Don't think so. Parv, you tell me what is your answer.
Of Rn.
Rn equals to how much?
Sorry.
H square epsilon naught by pi me, mass of electron into E square whole into n square by z.
Correct. Very good.
Also got the same.
Very good.
That's the same thing.
Yes, it's same.
Yes.
Very good.
Yes, sir, right. I told the energy answer by mistake.
You said e power 4. I don't know how you got e power 4. Okay. So this is the derivation of radius. And now you can find that once you get the radius, what is the energy relation? En equals to how much? You got En also?
Yes, sir.
How much?
2 pi k square m.
Okay. Right. Convert k into 1 by 4 perhaps not, because we always write in fundamental constants.
Sir, actually, I found it in epsilon naught, but because we are.
No. That is the better way of writing.
Okay, sir. So in just a second.
Yeah.
It is m e raised to 4 by 8 h square epsilon naught square into z square by n square.
With minus sign, right?
With minus sign.
Okay, so let's do everyone do the actual calculation of this value. Tell me how much you are getting after doing the substituting the value. M is how much? Let's calculate everyone this actual value. What is M?
9.1 into 10 raised to minus 31 kg.
And E is how much?
1.4.
What is epsilon?
10 raised to minus 12 and
What is H?
6.62 into 10 raised to 34. Minus 34 joule per second.
Now these values are also very important. That's why I'm forcing you to write. Okay, because when you do actual calculation, you need to know all these values. It may be given, it may not be given. I'm not sure. And who will do this calculation quickly? Take the values together, 9.1, 1.6 power 4. 8 into 8.85 whole square. 6.626 whole square. And take the power separately. So it's 31 minus how much? 76?
76,
Plus 68. Plus 24.
That's 24.
Okay, very good. Nice values. How much is that? This part is how much?
3.5 into 10 power minus 3.
3.5.
No. Only the value of the first one.
Value of the first one.
3.5 into 10 power minus 3.
And the power here,
Sir, minus 15
so it is 3.5 into 10 power minus 18. It must be in which unit?
joules.
But in which unit we represent the answer?
EV, electron volt.
Electron volts.
EV.
So how to get electron volt? Tell me.
Divide by 1.6.
1 point.
So
Very
10
good.
raised
Divided by the E value, right? So basically,
Yes.
we could have taken cube here itself, right? Anyway, you're getting the idea. So if you divide by 1.6 10 power minus 19, you will get EV, correct?
Yes, sir.
And how much is that?
35 by 1.6. So
It's a 35 by 1.6. How much?
Seven by
Sir,
0.
from 2.18.
So that means just your answer is incorrect.
It
check
should
it
be
again.
13.6, no?
Yeah, it should be 13.6, no?
Yes,
The
sir.
answer we know. That's why I'm saying, okay, do the calculation.
I made a mistake.
Yes.
Over
you
there
can.
is h square, right? I only took only one h.
It is power 4.
I did one mistake.
So 1.6 power 4 divided by 8.85 square divided by 6.626 square. It is
2 into 10
2.1679.
point minus 3, I guess.
Yeah, minus 13. Hmm. You can check how much you're getting. Guys, tell me.
Just a second.
Yeah. Yeah, 2.16 10 power minus 3. Yeah, and this was 10 power minus 15, no?
Yes, sir.
So 21 by 1.6. This is better.
216 by 16. Both are divisible by 4.
13.549. So that's very close to.
54 by 4. 54 by 4.
Okay. So you got the answer for the entire constant, and that is known to us, but still we need to do the derivation. Why? Just to get yourself familiar with all this calculation. You are going to face such calculation in examination. If you are not having the habit of writing so much thing, you may skip the calculation totally. So the EN will be how much? So it requires tremendous patience. Okay. So, okay, let me write down something here interesting. This entire term is called. So I'll write it once again. MEE4 below is how much? 8. 8 H square. This entire term is called how much? RHC. This is again very, very important for you. This entire term is called RHC. What is R?
Rydberg's constant.
Rydberg's constant. So there is a formula for the Rydberg's constant, and we write R infinity for a certain reason. Actually, I'll tell you why. So this is the Rydberg's formula. MEE4. Sorry. 8h cube epsilon naught square. See, it's very easy to calculate because the left hand side is how much? Minus 13.6 EV, and HC is how much? If you remember, 1240 EV nanometer. Understood?
Yes.
No, not understood. HC
Yes,
value is
sir.
how much? Always remember,
Ah.
HC is 1240 electron volt nanometer. You must remember this answer. Modern physics is all about calculation. If you're not good with all these ideas, it's very difficult for you to do the calculation. So how much we're getting R infinity? Okay, not minus, just this. So 13.6 is equals to EV equals to RHC. So you can see EV gets cancelled out. So you get 1 by 1240 nanometer, which means 10 power 9 upon 1240, which is how much?
1.1 into 10 raised to 7.
You can write it 10,000 upon 1240 into 10 power 5, right? Isn't it? How much it turns out to be?
Where did the 13.6 go?
I missed that part. Oh, I missed that part. Into 13.6, right? So how much this will come?
1.1 into 10 raised to 7.
That's the answer, if you remember.
Ah.
What I'm teaching you is how to do the calculation in situation, what to remember, what not to remember, what you can do the direct substitution, what you cannot do the direct substitution. Okay, so of course we're not supposed to remember this value, but we know this is equal to 13.6, so we can do those calculations. Yes, tell me, you were saying something?
So, yeah, R infinity will be meter inverse for this value.
Yeah, it's of course nanometer meter inverse. That's why the wavelength will be in meter. Or that's why we can express the wavelength of radiation in terms of Rydberg constant. Is this clear, guys, so far?
Yes.
So we got the energy relation. And now you will see some magic. So radius we have done the energy. Can we do the velocity quickly? For V, which relation will give me answer quickly?
MVR equal to H by 2 pi.
Yeah, I can get the answer quickly because I know the En. En is how much?
Z square by N.
This is the answer, right?
Yes.
So
Yes.
we know this entire term representing the kinetic energy, if you remember.
Yes.
Yes.
I'm done. So Vn square is how much? 13.6 into 2 into 1.6 10 power minus 19 upon 9.1 10 power.
Minus 31. Z by whole under.
So if I take the root and the root of this value, now you're supposed to remember these values. I definitely don't remember because I don't need to, but you guys need to remember some calculation already. How much is this calculation? Tell me, guys.
2.18 into 10⁶.
So it's good if you remember. Luckily, I also remember this value only. Okay. And once you know the Vn, you can find the omega n very easily.
Yes, sir. By Rn.
And we know both answer. So Vn we know 2.110⁶. And Rn we know
0.529 n²/z.
How much is that?
Roughly 4 into
4.1
10
16.
z²/n³.
Very good. Radian per second. That is correct, no? That is for 2.1 by 5.3. How much is that? Let me do this. Roughly, I just guessed 4.1. Less than that. Is it 4.2?
It's 3.9. sir.
3 point, yes.
3.96. So we can take 4 only, no? 4. So 4 into 10⁻16 is fine.
Yes, sir.
So the frequency of the nth order will be
Omega n/2.
so 4 by 6.28. How much, guys? Okay, so this turns out to be 6.3 10⁻15 hertz. So we got all the answer: frequency, omega, Vn, Rn, and everything else. If you know this way, then this is helpful. If you know only formula, not the derivation, and if JEE will make a twist into the derivation, then you will find it difficult. So the way you should learn it this way. You should know the derivation, and you should also know that which way to move ahead to get the answer as fast as possible. Okay. So keep in mind all this thing. Let's do something interesting about Bohr's theory. So for H atom, I'll come back to H atom. The energy of the nth orbit is how much, guys?
Z²/n.
EV. So what I'll do is I'll do the orbit level. And this is magic. Oh, you won't believe this is magic. So ready for magic?
Yes, sir.
Okay. So what is the energy of the first orbit for H atom? So for H atom, the formula will become
14.6/n².
so for the first orbit, the answer will be
Minus.
Minus
okay. I will not write EV and minus, and I'll just write the value next. The next is how much? Okay. What is the next?
Point something.
What is next? What is next? What is next? Next. 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 Maybe 7. How many of you remember this?
Sir, only the first 3.
This is so magical that you can remember everything. Let me show you. Close your eyes. Closed. Okay, before we close, let's do the calculation because even I'm not sure. I thought this should be correct. Just let's do the calculation and confirm it. Everyone. So I think first thing is
First and 10th can't be the same one, right?
minus 0 point. Good catch. So you will get the fishing award, because this was the good catch. Oh. Numbers play, no? This is like it turns like this way, that way. Okay, so close your eyes. It's not difficult. Okay, first verify. I think first is okay, no problem. Second is okay, no problem. Third is okay.
Yes, sir.
Yes, sir.
Okay. Oh, great. Third is okay. Then fourth is okay for sure, I think. Fifth is okay. Sixth is okay. Seventh is should be okay. Eighth okay. Can you confirm the last three?
So last one is okay.
Correct. Last one is okay. What is about the second last and third last?
We'll have to check.
Check.
Yes, sir. That's right.
Second last is okay.
Yes.
Third last.
Yes.
Fourth last. N equals to 7. Can you check, guys? N equals to 7.
Yes, sir.
Correct. N equals to 6. Correct. N equals to 5. Okay, I think all are correct. So do I really mug up these values, or am I writing by seeing at somewhere? The answer is no. I studied this in exactly, I can tell you, it was 2003. Month was January, and I was on my rooftop in the sun. The time was roughly 1 p.m. and I was reading through these numbers, and I don't know what happened. It got printed in my brain actually, and now the same number I'm going to print in your brain. It is really easy. So read the number. Okay, I will read in Hindi because that's how I studied actually. So the first number is 13.6. Okay, don't try to minus and all. So 13.6. Everyone, 13.6. Tell me 13.6.
Yes, sir.
Yes.
Say it with me. 13.6.
13.4.
3.4. Close your eyes. 3.4.
3.4.
The next number is 1.51.
1.51.
The next is 0.85.
0.8.
0.54.
0.54.
37272116. So simple. 37272116. 37272116.
3727 2116.
136.
136.
Now you can remember actually. You can revise without seeing the answer. You can tell me the answer. Is it happening with anyone? Able to recall everything?
One.
It's very easy. 13.6, 3.4, 1.51. Okay. 8554. 8554. See the rhythm. 8554. 8554. 37272116. 136.
Yes, sir.
Yes.
Do it once again. This is magic. This is magic. There's something in these numbers. I don't know what are these numbers, but these numbers are so fascinating that once you remember, you will never forget in life. There's something magical about them. I don't know. So close your eyes. 13.6, 3.4. Because the first difference is known to everyone. The third is 1.51. I'll tell you if you're getting confused, if it is 1.51 or 0.54 or 54. So 4 comes afterwards. So 51 is before and 54 is after. So that's why I remember 51 comes before. So 13.6, close your eyes, everyone. 13.6, 3.4, 1.51, 85, 54, 372721 116, 136. Done?
Yes, sir.
Yes, sir.
Yes.
Can you recall everything once again? Without
Yes.
seeing the answer. So who will tell me all numbers without seeing the answer? Raise your hand. I'll ask anyone. If anyone is willing to say, okay, Per will, okay. There are 2 participants. Mugdha also willing to say, okay, Manasvi, okay. Okay, I'll go with Manasvi. Okay, Manasvi, you will tell me the answer. Tell me. Close your eyes.
Yes.
Yeah. Start.
13.6, 3.4, 1.51, 0.85, 54, 3727, 2116, 136.
Very good. Excellent. Okay, clap everyone. Okay, so she has done marvelous job. You can clap for yourself also. I'm not hearing the clap sound. Okay.
You can see it.
Yeah, I can see it now. Very good. So do you believe that these are magic numbers? Because if it is not magical, it's very difficult to remember. But there is some rhythm, some flow in that number. And just you need to look at these numbers once in your life. You can always recall. And to solve question of JEE advanced or mains or whatever, or this chapter, you must remember these numbers. So these are numbers which you will remember. For any other item, what we do?
Z square ka factor.
We multiply with Z square. That's it. So if I have to write for the helium, I'll write the same thing. I'll multiply for every number. So into 4, into 4, into 4, into 4. So helium plus into 4. Lithium plus plus into 9.
9,
And radium plus plus
16.
that's it. No need to remember further, just remember these answers. So 13.6, 3.4, 1.5, 1.85, 54, 37, 27, 21, 16, 136. So these numbers, if you remember, you can write the transition energy for any element. Okay. Any means Bohr like atom. You can write it for helium, you can write it for lithium, you can write it for beryllium. What else we need to remember to master this Bohr's theory, which I realized as a child, as a student? You need to remember the difference as well. Okay. So we'll talk about the excitation energies. What is the excitation energy, guys? Amount of energy required to excite the electron from ground state to any higher state.
Yes.
Amount of energy required to excite the electron from ground. See, the beginning must be ground. If you go from 2 to 3, can we say excitation energy? Yes or no? If an electron goes from 2 to 3, orbit 2 to orbit 3, can we say excitation energy?
No, sir.
No, we cannot say. Excitation is always measured from the ground state, ground level. Okay. So these are some basic things you must remember. Excitation energy is always measured with respect to ground state. I hope this is clear to all of you.
Yes, sir.
Yes, sir.
So what is the meaning of first excitation energy? N equals to 1 to
2.
second excitation energy
1 to 3.
1, 2, 3.
1 to 3. Okay, that's too much. Third excitation energy and 4. That's it. I'll not go beyond this. Okay, now comes the mental power. 1 to 2. Which number to which number you're going? Minus 13.6
As 13.6
changes
to
to
3.4.
you need to give energy, no? Because that's decreasing. The negative is decreasing, right? We have to give
Yes.
energy.
Yes,
How much
sir.
energy you need to give? The difference.
10.2.
10.2 EV. It's very famous. What is the first excitation energy value for H atom?
10.2.
And then you know that He plus, Li plus plus, and Be plus plus plus. What we need to do? Into 4, into 9, into 16. The moment you see a number 40.8, what should click your mind? This is happening in He element,
Yes,
He
sir.
atom,
Yes,
He
yes.
plus. Because other energy, even it is not possible, because the first excitation is the biggest value. That is called the biggest jump actually. So going from 1 to 2 is the biggest jump. Every other jump is getting smaller and smaller and smaller. Do you realize this? You should.
Yes.
As you go above, the gap will merge, isn't it?
Yes.
So as you go above, the gap will become very small. In fact, as n will approach infinity, there is no gap actually. All energy level will collapse or coincide or merge together. Understood? So
Yes,
after
sir.
some point, the energy distinction will vanish. Okay. So how to find the energy difference of very large number of n? If I say find a energy of 49 and 50. If we do the actual calculation, we will go to hell actually. It's very bad calculation. So any trick for that, guys? There must be some trick. We'll come to that. So for first of all, what is the E2, guys? E2 is how much? You go from where to where? 1 to 3rd. Now there will be increment for sure because you are going to bigger level, but the increment will not be much. The first is the biggest gap. Second will be how much? Mentally do it. $13.6 to
1.5.
1.5,
1.
right?
Yes.
You know
Yes.
subtraction?
Yes.
Anyone know subtraction? Everyone knows, huh?
Yes.
No, these are not simple numbers. You are bound to remember these numbers. In examination, the moment you see the value in the question, they should click, okay, this belongs to second excitation energy. Oh, electron has gone there. Okay. So let me give you a question. You can do it mentally. So if I have an H atom in the ground state and I supply 12.09 EV energy, where will be my electron now? A ground state H atom is given 12.09 EV. Where the electron will be now?
Second excited state.
That is 3rd orbit.
3rd orbit.
Now the lifetime of an electron in the excited state is only 10 nanosecond. What is the lifetime of any electron in the higher orbit? 10 nanosecond. How big is 10 nanosecond? Oh, it's very small for us. Therefore, any electron cannot stay in the excited state for how long time. So what will happen? After 10 nanosecond, these electrons will
Come back to ground state.
come back to the ground. In the due process, what they will do? They will lose energy.
Radiate energy.
And the energy loss will appear as EM wave.
EM wave.
That is how the light is produced in actual. So the production of light is due to the excitation and de-excitation of electron. You can think that electron will suicide and this is the soul. H nu. Interesting. No? So the lifetime of any electron in the higher or excited state is very few, or it's very less. It's a in nanosecond scale. And after 10 nanosecond, they come back to the ground state. Therefore, even if we try to keep on exciting an electron every second, or maybe every millisecond, or maybe even microsecond, you will always find the electron in the ground state. Do you realize what I'm saying?
Yes.
Unless if I go beyond nanosecond. So if I am exciting any atom every microsecond, still every time I will see the electron in the which state? Excited or ground? See, you excite an atom from ground state, and then your next excitation is after 1 microsecond. So when you will go for the next excitation, where the electrons will be? In the
Ground
excited
state.
state or ground state?
Ground state.
Ground.
Very good. It is always in the ground state. Do you realize this? What I'm saying?
Yes.
Yes,
Yes.
sir.
Very good. You all must realize. Okay, E3 guys, what is E3? Tell me quickly. 0.85, 0.85, 0.85. So 13.6, 0.85. How much?
12.94. Sorry.
Okay, do the subtraction. Go back to kindergarten. Do the calculation. Okay, 13.6 minus 0.85.
5.
How much is that? Maybe I may be wrong. 0.85. How much is this? 5. 5 minus 8.
7.
5 means 15 minus 8. 7. Is this correct, guys?
Yes.
So you can see that the third excitation will be having somewhat more energy. And the E4, the last E4. 0.85, then 0.54. 0.54, how much? 13.06. Am I right? Maybe.
Yes.
Yes, sir.
So this 4 excitation energy you must remember, because, and not only this, when you see a question, you need to always do the calculation. Is it multiple of these numbers or not? Something like this. Modern physics is all about calculation, and not just calculation. You need to remember some of the calculation, because without remembering these standard calculation, it is very difficult to do the calculation. Solve the question. Because you're not supposed to use calculator in the examination. You have to do it very fast also, effectively also, in less time also. And if you start doing the actual calculation, imagine how much time it will take. At least 10 minutes to solve one question. Okay. After the excitation energy, we have to talk about ionization energy. I hope you know this. This I will not teach. Energy of ionization. What is the energy of ionization? What is energy of ionization?
Amount of
Required
energy, but
to
completely
electron from isolated gases.
Yes.
So it will be free from the boundation, isn't it?
Yes.
Yes.
Okay. So imagine an electron in the H atom is in the second excited state. What is the energy of ionization?
Exactly the energy of the second excitation.
And what is that value? Because you cannot say that in examination.
1.5.
How much?
1.51.
1.51. Correct. So second means third orbit, na?
Yes.
So the electron is in the third, which is 1.51 minus 1.51. So to free, you just need to give it positive value.
Yes, sir.
And also someone in the second excited state has taken already enough energy. So it has taken 12.09 energy, right?
Yes.
Yes.
So if you have taken that much energy, so the total energy required is 13.6. You have taken 12.09. So what is left also? 1.5. Okay. So energy of ionization is for the valence electron, and for single electron system, every electron is valence electron, right? If we talk about the single electron system, that itself is the valence electron, isn't it?
Yes.
That is the last electron. And therefore, if you know their place, if you know their excitation energy, okay, or they may give you that if the energy of ionization of an H atom.
Share map. I'll come in
Yes,
5
yes,
minutes.
yes. Yeah, sure. Okay. So the question will come like this. If the
I'm back.
sorry, yeah, if the energy of ionization of an H atom is 0.85, not 0.85, it's too small, 0.54. If the energy of ionization of an H atom is 0.54 eV, electron volt, so find the orbit of the electron.
5.
Simple, and you know the values, and you will face only these values. So the magical number is something which you need to remember. Understood? And then do the calculation. So I hope the energy of ionization is clear to all of you. Energy required to free the valence electron from the atom. Okay. So to make the electron unbounded or free. Okay. What is next? So this is done. We can go to the next concept actually. Or rather, we would like to solve some questions. So let's open this book for SC Varma. Okay, we can do something because you will also solve this. Number of spectral lines emitted by an atom. So here spectral lines means basically the number of photons, right? So how many photon will be or could be emitted by a group of atoms? It's very easy to do the calculation. You can do by permutation and combination. I'll show you for some. So how many is n equals to 1, 2, 3, 4, 5, 6, sufficient. So let's say an electron is in 6th orbit. Then in how many ways it can come down? 6 to 1 directly, or 6 to 5 and then 5 to 1. 6 to 2 and 2 to 1, or 6 to 3 and then 3 to further something more, or these are many possible transitions that a single electron can go from the 6th orbit. So once you reach the 5th orbit, let's say if someone begins from here, then again from 5th there are many ways to come down. 5 to 1, or 5 to 2, 5 to 3, 5 to 4. And those who are in fourth orbit can come down again in many number of ways. So 4 to 1, 4 to 2, 4 to 3. But once you're in 3, you can make multiple ways. So 3 to 1, 3 to 2. And once you're in 2, there's only one way. Every arrow represents possibility of a transition. And these are basically the count of number of photons, because every transition represents a distinct transition. Do you realize this? Every arrow is distinct. There is no repetition.
Yes.
So how many transitions you can see here? Can you count the transition? How many?
15.
So there are 15 transitions because you're going from 6 to so, sorry. So while going from 6 to 1, there are 15 possibilities or 15 ways of doing the transition. And that is why if you use the formula from the permutation and combination, what you can write?
6C2.
NC2.
6C2, very good. And which is again equals to 15, right?
Yes.
sir.
And you can exactly count. I have shown all the 15 ways. Now, this way of drawing is again important to you. Why? Let me tell you. If someone is knowing only this formula, can answer only one question. What? The number of transition. Okay. But I think you have studied in chemistry. That's why I'm not repeating this. I know you know the spectral lines, the types of spectral lines. Lyman. Then Balmer. Then
Fast.
then
Bracket.
Bracket.
then
Fund.
Fund.
One.
then
Something Mary or Berry.
I think Humphrey something like that. So okay, what is Lyman for?
From N to 1.
So you wherever you are, you come back to 1. So Lyman corresponds to the highest energy value, correct? So it means the final is going to be N to 1. What is Balmer?
N to 2.
N to 2.
So Balmer is only possible for 3 to 4, 3, 4, 5 and on. Question.
N to 3.
That's logical. N to 4 and N to. Okay, and that's too much. So Humphrey will happen. You have to go much beyond that. So in the Lyman series, the transition will take place from any way to 1. Okay. So how many Lyman series you can count here? Count the Lyman series in this transition, which I have shown from
5.
6 to 1. Exactly.
5.
Now, this is not possible if you know only formula, isn't it? So you need to draw this and you can understand that there are 5 possible transitions for Lyman actually. So number of Lyman series will be how much, guys?
N minus 1.
N minus 1. Now the thing is, instead of Lyman, what they will ask you? Find the number of UV photon. Because anything Lyman is UV rays, right? Or UV radiation.
Yes. For hydrogen atom.
For H atom. So because everything is UV, so I can ask you find the number of UV photons. And the answer is 5. So you need to know, okay, these are the ways of asking question. What is how many visible lines there? Number of visible lines? Come on, guys, tell me. Number of visible lines.
4.
So visible means Balmer.
Balmer.
1,
Balmer 4 or
3.
Sir, but
Yeah.
sir, in Balmer also there are 4 specific wavelengths, of visible light.
So all are Balmer, no? All are visible.
Okay. Acha, first 4. Yes,
These
yes.
four.
See, I have tick mark. Okay, so everything coming to the n equals to 2 is Balmer,
Yes, sir.
and anything coming to will be always visible component of light. Understood?
Yes, sir.
And now that is very interesting. As you go up, you can see it will decrease by 1. So then in n3, how many you can count?
3.
3. Then
Three.
next 2, then 1. So the formula is simple. N minus 1, n minus 2, n minus k. It is clear?
Yes.
So for a small question, see, you will never get question more than 6 actually. That's why I always for 6 only. So for any question up to 6 or 5, you should better you should draw it and then count it. It's very easy. And how to draw it? So you have to start from the highest value, go to every level down, down, down till you go to the next value. Then you start from the next level, make it all such arrangement, and then next, you will see it's very easy to draw. Okay. What is the energy difference? I mean, now we know the energy difference. We can write the relation. Energy of transition in Bohr's atom. I hope this is very simple. That's why it will not take much time for you to understand. So if you go from N to M, oh, it's like N, no, it's fine. N, then M. I is M. So if electron will go from M to N, it will release energy, correct? So what is the energy difference? Delta will be energy of M minus energy of N.
Yeah.
And energy of M is how much?
Minus 13.6 Z square by M square.
So you get the answer 13.6 Z square 1 by N square minus 1 by,
M square.
and every transition will convert into EM wave. So this will be equal to how much, guys?
HC by lambda.
And if you remember, I told that this value is called RHC. Do you remember this?
Yes.
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 So R
you are-
infinity SC
Infinity.
into Z square is SC by lambda. Yes, Parag, tell me.
Sir, you are going to tell the reason for that infinity.
I'll come to it. Correct. Okay, it is called infinity because in the Bohr's orbit, we assume that the nucleus is at rest and electron is orbiting it. But if you remember the binary star system, which we studied, there we assume that both the mass will move around the common center of mass.
Yes,
So
sir.
here infinity means the other mass is infinitely large. That's why it's called infinity. The moment we go to the Bohr's modified Bohr's theory, in which we are going to assume the motion of nucleus as well. So there a reduced mass will come into picture, and R infinity will be replaced by R mu. Okay, so I'll come to that. So we are not
there's
studying
also
the
symbol
modified.
RH that is used, right?
Pardon?
There's also symbol RH that is used.
Yeah, so that RH basically belongs to the R mu only.
Okay.
R infinity.
That's
So
all.
1 by lambda is how much, guys? R infinity. And again, see the usage of R infinity is very much ambiguous. Many texts only use R, like in JEE textbook, you will see only R. Very few text has mentioned this clearly that you should use R infinity and R differently. Okay, very few. So 1 by lambda is how much, guys? R infinity Z square 1 by N square minus 1 by M square. This is called the Rydberg's formula. I hope you remember this.
Yes,
Yes.
sir.
Yes.
Now the other way around is you only remember the Rydberg formula, rest you can derive by reverse process. Why? How? To get energy relation, multiply by HC both sides, because SC by lambda is called energy. If 1 by lambda is this much, then SC by lambda will be energy, right? So this is easy
Yes.
to remember, and you can go back and get the answer. For every spectral series, which you know, Lyman, Balmer, Paschen, there is a series limit, which is also, I mean, asked. So do you know from chemistry, or shall I teach it? No.
Sir, we know.
Yes. Yes.
So you know the series limit, everyone, guys?
Yes, sir.
Series limit of every. So we have UV rays, we have visible, and then everything beyond is infrared. So we have near infra,
Yes.
far infra, very far infra, very far infra. So it's just a name actually. So we have three types of component. We have UV, visible, and everything else beyond the Balmer is infrared. Okay. And why it is infrared? For the obvious reason, it's a small range of energy difference, and that's why the energy is very small, and that's why it's infrared. Okay, I was telling you that how to find the energy difference of two far points. Let's say this is n, maybe in thousands. This is n plus 1. Or I'll just write n and n minus 1. So how to find this energy value? And how to find the energy transition of this from here to here? Okay.
Sir.
Hmm.
Delta n into delta n plus 1 by 2.
So the delta E is how much? The delta is how much? R HC 1 by, tell me guys how much?
1 by n square minus 1 by n minus 1 square.
Right? Is this clear?
Yes.
Yes, sir.
Yes.
There are two ways you can do like this. You can take n common. Because n is very large, so 1 by n is very small.
Yes.
So we can use binomial approximation 1 plus 2 by n. So this is the answer. Very interesting answer. If n is very large, you can use this formula for energy difference. For n. So what is the answer here? If I tell you find the energy difference of 50 to 51, don't use 50 or 51, just put a 50Q, that's it.
Yes,
Understood? Not
sir.
understood.
Yes.
Understood.
And basically this is 2 into 13.6 by n cube EV. So it is how much? 27.2.
20.
So if someone is asking you find the energy released, find the energy released between two transition. Let's say 100 at 299. A simple question. So I should put any question how much, guys? Yeah, 6. So how much is the energy difference?
10 to minus 6.
Really small, right? I hope this is clear. 2.7 to 10 power minus 5 EV. So okay, this is, I mean, there's one more way of doing it. You can differentiate the function and you'll get the answer. Okay. So the other method 2 will be, because we know E equals to how much? So d by dn equals to, tell me guys, d by dn equals to how much? Is this clear?
Yes, sir.
Yes.
So the delta E will be how much? And delta n is how much? 1.
Yes.
dn is 1. Because we're taking only one difference, right? So this is the other way of derivation. I hope you understand this. Or is it
Yes,
difficult?
sir.
So
Yes.
either do by the binomial or do by this differentiation, because it's a very large number and d is very small. We can do all this calculation. Okay. So this is simple. Okay. In the Bohr's theory, what else you need to know? Should we practice something or should we go for more theory?
Theory.
More theory.
Yes.
So then you can practice at home. Okay. Our next lecture will be like doubts and discussion on Bohr's theory.
Yes,
Okay.
sir.
So we can go to something somewhat advanced theory called the modified Bohr's theory. So imagine if I have a hypothetical atom. And in this hypothetical atom, the orbiting particle is no longer electron. So I introduce a new particle to all of you called muon. So muons are short-lived particle and it comes from the cosmic radiation. And many times it enters the Earth atmosphere and reaches the Earth's surface also. So it was long time. I mean, it was very interesting history actually that muon enters the atmosphere and comes to back to the sea level, because it is received in the lab, which is in the sea at sea level. So cosmic radiation happens almost 10 kilometers above the Earth's surface. Okay, 10 kilometers. And the lifetime of this muon is microsecond, something microsecond, I don't remember how much. So it is expected that in that much microsecond, muon cannot reach Earth. If the lifetime itself is in microsecond, and if it is 10 kilometers away, it should never reach the Earth, but nevertheless, it reaches the Earth. And that was the, you can say, mystery for a very long time, till Einstein gave the theory of relativity, in which we came to know about something called time dilation and length contraction. So in muon's frame of reference, because muon is a very fast moving particle, it moves close to the speed of light. So in the muon's frame of reference, the Earth is moving towards the muon, right? If I am moving towards you, then you are moving towards me. Same thing.
Yes.
So in the muon's frame of reference, the Earth was moving towards muon, and therefore the distance as appeared to the muon was not 10 kilometers, it was rather 2 kilometers roughly, or 2.5 kilometers. That is called the length contraction. But in the Earth frame, because muon is moving, the lifetime of muon in the Earth frame is much more than the lifetime of muon in the muon's frame, which is few microseconds. And this phenomenon was called time dilation. So time will slow down, or you can say a moving clock will tick slower. That's a, you can say, a statement. A moving clock ticks slower. A moving object appears smaller. So everything which is moving appears smaller. Everything which is, I mean, if a clock is moving, it will tick slower. So time will dilate and length will contract. So there are two phenomena in relativity which we'll study also: time dilation and length contraction. And these two phenomena actually was consequence of Einstein theory, which was able to explain this paradox: why muon comes to ground. Okay. Anyway, so we'll see a glimpse of relativity before the EM chapter. But imagine if I give you muon. So mass of muons is roughly 200 times mass of electron. And we know that the mass of proton is how much?
1.67.
1837 times mass of electron, right? But you can see clearly that when we compare the proton with electron, it is really very, very heavy. But if we compare proton with muon, it is roughly 9 times, huh? Isn't it? So we have
Yes.
one object M, another is 9M. You can think this way. Now saying that this will revolve around this is wrong, because now both are heavy. And if you know physics, it says that how it will move now. So
Around the
two
common center.
massive atom, massive mass will move under their mutual interaction about the common center of mass. Understood? So
Yes, sir.
we need to change this entire Bohr's theory as per this new revelation that the motion around the nucleus is incorrect interpretation. Then I need to move around common center mass, and then this kind of diagram is also misleading. So I will not draw this diagram. So I'll draw a fresh and more accurate diagram for you to understand. So imagine this is the nucleus with a positive charge, and the revolving mass, or the mass which is getting attracted, is also not very light. So the negative charge is also here. Okay. And the charge here is ZE. And the charge of muon we still take minus. So that's very interesting. The charge remains same as electron. Okay. So these are charged particles. And now the distance between them in different excited state will be different. So we can still call Rn. But Rn is the distance now. Don't call it radius. Okay. That's a bad way of saying it. So what is Rn here?
Distance.
So in a different excitation state, it will have different separation. So I'll replace the word radius by separation. Okay. So of course, I mean, if this is MP, sorry, what is the mass here? No, mass will be how much? Aman, AMN. A is the A is what? Atomic mass number, isn't it? Now, what is happening here? The mass of the nucleus will become important here. So far, we were not considering the mass of nucleus, right? Now we need to know the mass actually, because we are doing the modified Bohr's theory. So for simplicity, I will bring this capital M, I'll call this small m. I hope this is clear. If you want to write the capital M, how to write? Roughly we can write 8 times mass of neutron,
Yes.
because mass of proton is roughly same as neutron. So we can add the atomic mass number into mass of each nucleon equals to mass of the nucleus. Roughly, we can tell this. Okay, anyway. And M will be given to you. So M is here at twice at 200 mass of. For some situation, if I'm taking mu on. So for simplicity, I'm taking the ZE minus E, capital M, small m. So center mass will be somewhere here. And we have done this in electrostatics. Come on.
Yes, sir.
So this will move, the nucleus will move in this small circle. And the negative charge will move in the big circle, right? So at any instant, both will remain on the same line. So negative charge will be here. And this giant will be here. Okay. So we all know this. We know a lot of this. So what is the moment of inertia about the common center mass? What is ICM? So we can write reduced mass, answer directly. Reduced mass into Rn squared. Do you remember this formula? Hopefully you know. So what is reduced mass?
Yes.
Product of mass
Mm upon M plus.
basically inverse of reduced mass is sum of inverse of masses. So it is called reduced because it is less in value compared to each mass. So reduced mass is less than the least value, right?
Yes, sir.
Yes.
Okay. So ICM we can write directly for the two particle system about their common center mass directly by the formula. No need to derive, you can remember this. Okay. Or you can read in rotational dynamics. Okay. So once we do all this thing, there are two ways of solving. Either you solve from scratch or be smart. So smart means every question we can solve only by modifying the Rydberg constant. Okay. So what was the energy relation? Do you remember this?
Yes.
Simply replace R by now the question is how to get R value. So if you remember the Rydberg formula which I derived somewhere, I said very, very important. Where? Do you see that R is proportional to M?
Yes.
Yes.
Yes, sir.
Basically, R is proportional to mass only. So what you will realize that
We'll multiply mu.
R mu upon R infinity is mu by M. That's it. This is the conversion factor. In fact, I can give you this as homework. You can try at home, try to derive formula from scratch, and you will get this answer. Okay, this is delta basically. Okay, anyway, I'll just I'll make it correct. So the moment you derive the new formula, you will see that everything can be replaced in terms of old formula by this relation. If you remember that R is proportional to the mass, of a moving system. So in case of one particle system, we take R infinity because other mass is infinitely large, we take. In case of a binary system, in which you move around the common center of mass, we take the reduced mass. And therefore, the R infinity you can replace as me R mu by mu. Am I right? So wherever you see this R infinity in the old formula, just substitute this answer, you're done. In fact, we'll get question based on this formula itself. Due to lack of time, I'm not deriving it. So you can practice at home and you can derive it. Is this okay?
Yes.
So will you try at home?
Yes, sir.
Yes, sir.
Okay. Now there are three concepts which is really advanced and you need to know actually. This is called atomic collision. Okay, now things will move really fast. So the base is given. You can start the solving SC Verma first. So you will attempt the SC Verma today, tomorrow, till next week. And next week I'll teach you atomic collision in detail. We'll go for X-ray also, because we will have some time to do the X-ray. Or if you can wait for half an hour, I can teach atomic collision. Choice is yours.
It is fine, sir. You can teach now.
And not it should be fine for everyone.
You can do.
Yes, sir, you can.
Okay, fine. Okay. So atomic collision. Okay, we need to know that, okay, when there is a normal collision in our day-to-day life, we say that, okay, heat is produced due to collision. If it is not perfectly elastic collision, right?
Yes.
So imagine if two atoms, okay, what is the heat basically mean? It means the surrounding air molecules will get up your energy and will move away. Heat means the atom of the crystal or the substance or the object will take up that energy and will vibrate faster. So basically heat is nothing. It is simply a way of saying that this energy is taken by the microscopic particles and it is difficult to snatch back from them. Although there is a method of getting back from fluid and gases, but not from all. For that, we have something called heat engine, in which we get the energy back from the molecule and we do the mechanical work, then we run the machines. Anyway, imagine if atom is hitting another atom in empty space. There is nothing in between. There is no molecule. There is a complete vacuum. Can we talk about heat there?
No.
The idea of heat will vanish. If atom will hit the atom, then you cannot talk about heat actually. So when there is a collision of atom with some particle, generally we talk about the neutron, because to create the transuranic elements, it is generally bombarded with the neutrons, and moderately moving neutron is readily absorbed by the heavy nuclei, which creates a you can say unstable nuclei or a meta form, and that subatomic nuclei means sub unstable, you can say, or unstable nuclei will further decay back into more stable one by undergoing fusion reaction, and in that due process we create some new element also. Okay, and if it is stable, then we get some transuranic elements. So if it is having the lifetime up to few microseconds, we say, okay, it will exist for that much time and it will decay. Okay. So many Nobel Prize in chemistry has gone in creating this transuranic element. Okay, so element after 108, all are having name of the scientist who created it. mostly actinides. Okay. So in atomic collision, what will happen if there is a collision? What do we expect? Heat is the gone. It is not going to come in picture at all. So what will happen? In atom, the only thing which can happen is excitation or de-excitation of electrons. Understood? So when collision will impart some energy to the atom will take that energy and will undergo excitation. Understood? And it may de-excite and come back in no time. So in atomic collision, the energy is either taken by the electron or it is not taken at all. Our syllabus is very simple. We talk about the collision of ground state H atom, ground state with neutron. So let's say the neutron is coming with velocity v, and that's called the mass of neutron is m. What will be the mass of this atom? Tell me, guys, what is the mass of this atom? Am I audible?
Yes, sir.
So what is the mass of this atom? If the mass of neutron I call m, what is the mass of this atom?
M.
M itself, no? Both are same mass roughly. Isn't it?
Yes. Yes, sir.
Because the H atom will have only proton,
One
and
proton.
neutron is only neutron. So both are having same mass. Okay. Okay. In every collision, what is conserved? Tell me.
Momentum.
Momentum is conserved. So that will
Yes.
be true even for the atoms. Atoms cannot violate the conservation of momentum. Okay. Atom can violate the conservation of mechanical energy. That's okay. But atom cannot violate conservation of energy. So mechanical means what? Potential and kinetic. That is violation is okay because there are many forms of energy. Okay. So conservation of momentum is always true. Conservation of mechanical energy is not required because I can change the configuration. I can take away the electron. But the conservation of energy is always there. So these are fundamental conservation laws which cannot be violated by anyone, including the atom. Okay. So if this M is going to hit this M, so what is the energy that can be used by the electron to get excited or to go transition? Which energy we can use? Okay, first of all, what is the energy of the system? If I take these to a system, what is the energy of system?
Half mv square plus
That's it.
plus 0. Yes.
So the ground state, it is at rest. So ground state H atom at rest. So what is the initial momentum?
mv.
So we can solve in two ways. One is the direct, the scratch method, or there is the CM frame method. So initial momentum is how much? mv.
MV.
Okay, very good. So what is the velocity of center mass? What is the velocity of center mass here? Tell me, guys. How much?
V/2.
Correct. It's V/2.
Yes.
In any collision, what remains constant? Momentum. And
Yes.
momentum conservation is equivalent of constant velocity of center mass. In collision process, can we change VCM?
No.
We cannot change VCM because VCM can be changed only by external force, and the collision is which force?
Internal.
Internal.
So internal force cannot change VCM. So VCM will continue with V/2. So what is the kinetic energy of center mass, guys? Half mass of system
V square by
into
4.
VCM
V
square.
square by
So it is mv square by 4. Isn't it?
Yes.
So
Yes.
out of total energy, this much energy is kept by the center mass. Can we take this energy away?
No, sir.
So what is the energy available in CM frame?
Half mv square by 4.
So we can write kinetic energy available one by 4 mv square. Yes or no?
Yes,
Yes.
sir.
If I assume the kinetic energy of neutron is k, I can write this also as k by 2. Yes or no?
Yes. Sir.
Yes.
Yes, sir.
So if electron wants to either get excited or whatever, which energy it can consume? Total energy or only energy available in the CM frame?
Available in the same.
Available.
The reason is the remaining energy will be required to conserve the momentum.
Of the momentum.
Do you realize this?
Yes.
Yes, sir.
So in any atomic collision, it is the CM frame energy which let electron undergo excitation. Is this clear?
Yes.
Yes, sir.
Okay, very good. Okay, so how much energy we have for the excitation? K by 2. So we'll take some cases. So energy. Okay, I have written this now. Available. Okay. So energy available for excitation of electron equals to how much? mv square by 4 or k by 2, where k is kinetic energy of neutron. Is this clear, guys? Is it
Yes.
clear?
Yes, sir.
Okay. So therefore, just a minute. So energy available for excitation of electron is k by 2. Now we have to ask ourselves, if k by 2 is less than E1, what was E1? Do you remember what is E1?
Yes, sir.
E1 is called first excitation energy, right?
Yes.
If this is not even sufficient for first excitation energy, what will happen?
Sir, nothing.
electron will never take this energy. Yes or no?
Yes.
sir.
Yes.
Because this is of no, this energy of no use. Okay. So energy will not be taken. So if you go to railway counter to buy a ticket, if the price of ticket is let's say 100 rupees, you have only 50 rupees or 80 rupees. You have to go back. You have to go back to your home without the ticket. So basically, there is no interaction between you and the atom. So if the neutron will carry energy in the CM frame, sorry, if the energy available in the CM frame is less than E1, then neutron will hit and will come back, and they will move as per the rule of conservation of momentum without any excitation. In such case, the sum of kinetic energy of the two particles will be equal to what? The initial kinetic energy of the neutron.
Total
And this is called perfectly elastic collision in case of atom.
Yes.
Because the energy in the CM frame is not utilized, so we call it perfectly elastic. Because in
Yes.
perfectly elastic collision, we only check the CM frame. Here, we don't talk about the coefficient of restitution that is meant for surface, and surface itself is infinite atoms. Here we're talking about atom itself. So in atom, you will never talk about the coefficient of restitution. Never ever talk about that. That's ridiculous. So this scenario is called perfectly elastic collision. And because it is perfectly elastic collision, what will happen? What will happen? So once the neutron will hit that, once the neutron will hit the atom, neutron will come to rest and atom will go away
Will move with the same velocity.
with the same velocity, because here mass is also equal, luckily.
Yes, sir.
Or you can solve by the basic conservation of momentum. But here you have to write the energy relation, which will give you the same answer. Okay. Because we can also derive the coefficient of restitution from energy, if you don't remember, or if you remember. Okay.
Yes,
Yes.
So
sir.
here the simple thing is, because here the mass is equal, so neutron will come to rest and the atom will go away, and atom will remain in which state?
Ground state.
Ground
Ground.
state C.
Ground.
So this is very unique. So this will remain. So atom will remain in ground state. Now the case 2. Let's say if K/2 is exactly equals to any excitation state, I can say J1, I mean J. Yeah, EJ. EJ means 1, 2, 3, where if it is exactly equal, then what will happen? All of the energy will be consumed by the electron and it will go to that
Yes.
level of excitation.
Sir, but how can we say that the energy from the collision is going to the electron only?
No, you are not getting it. If the energy in the CM frame is exactly equals to any of the excitation state, energy will be absorbed. Because that is not going to affect the conservation of momentum. Momentum is still conserved because the energy required for momentum we have separated out.
Yes.
So where we are dealing with the energy in the CM frame. Apart from the momentum conservation, what else energy you have? K/2
Yes.
or mv²/4. Now these are the rules. You need to remember this. How it is happening, I don't know.
Sir,
Yes.
so like, how does the electron know, like, at these intervals, there is an orbit? So, matlab, will it take the energy or not?
That's why I said we don't know about any of this. We need to remember that, okay, if this is the kind of case, then we have to proceed this way. So
Okay.
if the energy, which is k by 2, is exactly equals to the any of the energy of excitation, how they come to know, I don't know. Okay. But if it is, maybe it is practically observed, and that's why it is said. So the moment this energy is equivalent of any of the energy of excitation, 1, 2, 3, 4, 5, whatever, then all of the energy will be taken by the electron and will go to the excited state. And because all of the energy in the CM frame is consumed in this due process, such collision is called perfectly
Inelastic.
inelastic collision. Okay. And comes the case 3. If k by 2 is more than some excitation energy and less than the I plus 1, or it's a j. So it is more than j, but it is less than j plus 1. What will happen here? So k by 2 is more than, let's say, E1, but less than E2. So the
Same like
atom will take, atom will, because it is more than E1, but less than E2. So it will go to the first excited state, and the remaining energy will be available as kinetic energy. So partially energy will be absorbed, partially will be left out.
Yes.
Because you cannot go to 2, but you can at least cross E1. Na? So because the first condition is met, the electron will take the energy and go to the first excited state, and energy is more than first. So this is called
Partially elastic.
partially elastic collision. Okay, I hope this is clear.
Yes.
Clear to everyone?
yes, sir.
Okay. So again, there is some part which is still left. So next lecture I'll come with problem, and because this is important, so we will solve question on this topic, this particular concept actually. And there is one more collision that we need to discuss: collision of atom with photon. And there also we need to talk about the momentum and so on. So that I'll cover in the next lecture, because now I'm also tired. So see you guys in the next lecture of modern physics. You can start solving SC1. So your next lecture will be doubt lecture.
Okay.
And atomic collision is part of JEE syllabus, but it is not mostly in the SC1. So you won't get question of this in SC1. So I'll give you questions separately in order to practice. Okay, guys.
Yes, sir.
Yes.
So bye and take care. Good night.
Bye, sir. Thank you.
Goodbye.
Bye, sir. Good night.
Bye, sir.